Okay, let's pick up where we left off yesterday. We have to do part B of example 3. We've already got our factored function there. And then we're going to take a look at just a different version of this same question where we have to identify the vertical asymptotes ourselves. But one of them, which is going to be a little bit different, is going to involve the tangent function. So that's going to be the major new thing for today. It is not the most ideal thing for me to be doing, in a classroom alone, recording for you guys to see in the morning. It's much better if I can at least, look at your faces to see, any sort of understanding. This is something we'll do a couple times. So this last problem we do will be a technique where we'll repeat it a few times. So it's kind of just like one little extra thing tucked in these problems. But let's take a look at letter B first. It's in factored form because there's a couple points I want to make with this as far as making our sign charts. So we have our function f of x. It is made up of x plus 3 times x minus 1 squared. And then we've got another x plus 3 but squared in the denominator and x minus 2. When we go to find these limits, when we go to cancel, what's going to happen here is even though x plus 3 is a factor that cancels, when we cancel it, it's not going to completely be out of the denominator. So kind of taking a look at x going to 3, when we go to find that limit, sorry, let's do it this way. When I do the cancellations, sorry, I was trying to say something that I didn't have a picture to show. So when I go to do those cancellations, x plus 3 is completely out of the numerator, but it is not completely out of the denominator. So we are, in fact, in a non-zero over 0 situation, which is telling us that our side limits are going to be infinities. That should be clear from that, right? When we cancel the x plus 3 out of the top. That cancels one of those x plus 3s out of the bottom. Okay. So we need to make a sign chart for what we have left. We can ignore some of those x plus 3s. That's fine. I'm going to make a sign chart for basically what I have left after I made the cancellations. So I've got to find all the important numbers, all the numbers that make either the numerator or denominator 0. This is going to be a sign chart for f of x. They essentially do have the same, even canceled, they'll still have the same signs. They're still the same graphs. I've just possibly plugged a hole by making a cancellation. In this case, I haven't even done that. Anyway, so those numbers are -3, 1, and 2. I need to take piece by piece each of my factors. This is where BC got it wrong, even though I showed them this. So just keep this in mind. In the numerator, I have x minus 1 squared. That's equivalent to having x minus 1 times x minus 1. That's two separate factors. That means I need 2 green plus or minuses for that x minus 1. Numbers less than 1 are going to make it negative. So I'm going to put 2 green minuses there. Because we're less than 1. I'm going to put 2 green minuses in that section because we're less than 1. And then I put green pluses in all of the sections that represent numbers that are greater than 1. Those green pluses have done nothing for me because all I've done is put an even number of the same amount of signs. They're just telling me all positives. You are, if you understand why, allowed to leave those off of your sign chart. But that's just one more thing to think of, so I don't really suggest it. But I want to acknowledge it too. They are giving us no information. They are not changing our overall signs. I'll move on to my 2 bottom factors. X plus 3 will be negative anytime my number is smaller than -3, and positive anytime I'm after -3. And then my last one, which is x minus 2. That's going to do the same thing, but at the number 2. So anywhere on the number line that's smaller than 2 is going to be negative. after 2 will be positive. So hopefully I don't believe I've made any mistakes there. Looks good to me. My overall signs here are going to be positive, negative, negative, positive. This is what's going to allow me to figure out my signs for my left and right limits on 3 and my left and right limits on 2. Both of those functions or both of those limits do not exist because 3 and 2 do not make the numerator 0. They both can be plugged in the numerator and get a non-zero result, but they both make the denominator 0. Not sure why I have these 2 sets of limits out of order, but with 3, I decided to go 3 right, 3 left, 3 overall. And I know I'm saying 3, but I mean negative 3. So 3 right is over here. Those values are all negative. So if it's going to infinity, it has to be going to negative infinity. 3 left is on this side. Again, all the values to the left of negative 3 are positive according to my sign chart. And if it's going to infinity, then it has to be going to positive infinity. And when we're in that case, we do not write, when we look at the overall limit, the best we can do is write does not exist. Okay. 2, again, for the same reasons. Plugging 2 in the numerator is going to give you a non-zero. Plugging 2 into the denominator is definitely going to give you 0. So when I go ahead and do that, I know I'm going to get, that's telling me that I'm going to get infinities. I've got this set up differently. We'll do 2 left first. I'm going to skip to the middle, do 2 left first. That's negative infinity. Do 2 right second. That is positive infinity, which makes the overall does not exist. I think my thought behind, I either just straight up goofed, not going to lie to you on that one, but I think my thought there was that, if the limit was presented this way, you would have to know to write those 2 things next. So, really the difference between these 2 columns is me walking you through it versus me not walking you through it. One thing that I was thinking as I was saying that about 2 is, when I'm talking about non-zero over 0, in both cases, I'm talking about my simplified limit. Oops, sorry about that. Because my unsimplified limit, at least for negative 3, would actually give me 0 over 0. So these guys, I was getting an indeterminate form plugging into the unsimplified. So I can't use that. That doesn't tell me anything. I have to think about plugging into the simplified. So just in case anybody was thinking that maybe they were getting 0 out of the numerator as well, why was I saying that with negative 3? That's because I was looking at the simplified version. So in this case, we did factor and cancel, but the result was still does not exist. You don't know until you actually do those cancellations in a problem like this. All right, and then last but not least, just for clarity here, 1 was an important number, but it wasn't hard to find the limit because it was just direct sub. The opposite is happening. Plugging 1 into either numerator, the canceled or the non-canceled one, gives me 0. And plugging 1 into the denominator is definitely not going to give me 0 because neither of those 2 things would be 0. So that limit is just plain old 0. All righty. Example 5. Oh, take a breath. Example 5 is just going to ask this question in a different way. If you're asked to find the vertical asymptotes happen when your function goes to either infinity or negative infinity. It only needs to happen on one side of your x value. So you might be asked to do 2 things. Identify the vertical asymptotes. Just find a spot where you would be writing infinity down. If they ask you to justify, then pick one of those sides and write infinity. And write out the limit. That's what I'm going to show you here. Okay, so our first function is just kind of like what we've been doing. F of x is 1 minus x squared. and the over x squared minus 6x plus 5. Both of those factor. A couple different ways to think about 1 minus x squared. It's just our normal pattern, but reversed. So instead of writing x plus 1, x minus 1, you can write 1 plus x, 1 minus x. That follows the pattern. That works. If you FOILed that out, you would get 1 minus x squared. No surprise in the denominator, we're going to get one of those factors in some way, shape, or form down at the bottom. I get x minus 1, x minus 5. We've talked about this before. None of those match perfectly, but 1 minus x can be changed into negative 1 times x minus 1. I'm going to change it like this and put a negative out in front. Don't lose that negative sign. I'm saying that to you guys. I'm saying that to myself too. That's going to be important. So you could take a look at this. You should be able to see what's going to completely factor out of the denominator and what's not. The only possible answers are x equals 1 and x equals 5. But we know that if we take the limit as x approaches 1 and we go to factor and cancel that, we end up with we still have our negative. We have 1 plus x, and we have x minus 5. And that comes from canceling the x minus 1 here with the x minus 1 here. So this limit exists. This is negative 2 over negative 4, which is 1/2. So because of that, we're going to cross out x equals 1 as one of our possibilities. The limit exists, therefore the function is not growing without bound, so we don't have a vertical asymptote. That does not need to be shown if this is the problem that you have to solve. What needs to be shown is the vertical asymptotes, and the vertical asymptote is going to be x equals 5. That you can't cancel the x minus 5 out of the denominator. So let's make a sign chart for our function. And I wasn't just making that weird factorization on top to confuse you, but this is also important. That negative is really important for our sign chart because it is still a piece of our problem. So I'm going to make a sign chart for f of x. I'm going to label it. I can do it for the canceled version of it. So I could include 1, I could leave 1 out, but those x minus 1s, because they completely cancel out of the numerator and the denominator, I only need to worry about 3 pieces: the negative, the 1 plus x, and the x minus 5. I did want to do those in different colors. The negative, the 1 plus x, and the x minus 5. That negative doesn't have a 0 attached to it, so my numbers are just negative 1 and positive 5. So I'll put negative 1, positive 5 here. And I do need 3 signs. There is a negative in that numerator, so all 3 sections need to have a negative sign. I can now do 1 plus x. When I do that, I'm going to do a negative before negative 1 and a positive after. And now I can do my denominator. That's x minus 5, and that's going to give me negative before 5 and positive after, making my overall signs negative, positive, and negative. Okay. I know there's a vertical asymptote at x equals 5 because x minus 5 did not cancel out of the denominator. All I need to do is state that and write one limit statement involving x equals 5. So there is a vertical asymptote at x equals 5, and that's because your choice, the limit as x goes to 5, left or right. I think I went left the last time I did this, so let's go right this time because it doesn't matter. Of our function is, so come in from the right, negative infinity. Your choice. I could have said 5 minus is positive infinity, but I'm just grabbing these things from the sign chart. The problem isn't any different. It was our job to decide what our asymptotes were. If you're not 100% sure, like I only have 3 things underlined in my my function there and why I didn't leave the x minus 1s, think about what would happen if I included my x minus 1s in that sign chart. I actually would have to put in a whole different number. I'd actually have to add a positive 1 here as well, but I'd be adding negatives and positives. So I'll do it without writing them. I'd be adding like a negative and a negative towards the left and a positive and a positive. So anything that's completely factored and canceled out gets to stay out of that sign chart. Now, in my above example, x plus 3 didn't completely factor and cancel out. So I still needed it, but the x minus 1s completely factor and cancel out. Okay. All right. Last example, this is going to be sort of the oddball example. We are going to do something a little bit different here. I'm probably going to draw all over that line I have at the bottom of the paper. Vertical asymptotes happen when you end up with a non-zero numerator and a 0 denominator. So our function here is the tangent of 3x. Tangent, by definition, can be got from sine and cosine. You can rewrite tangent as sine over cosine. So the tangent of 3x, and there we go, 3x is our argument, is also sine of 3x over cosine of 3x. So these questions come down to asking ourselves, when is cosine 0? And to figure that out, we have to think a little bit or remember back from pre-calc about the unit circle. We will talk more about the unit circle later in the year. Right now, we're just going to look at the sort of easy part of the unit circle, which is where are the zeros and where are the ones. The unit circle, if you remember, is a circle on an xy axis that has a radius of 1, which means that this point is 1, 0. This point is 0, 1. And then these are sort of matching, except the 1s are negative. Negative 1, 0, and 0, negative 1. The unit circle can help you find the sine or the cosine of a value by reading those x and y coordinates. Each one of those represents the cosine of some angle. I'm just going to use theta since we already used x there. And the sine of that same angle, theta. And in a simple world, we would just think of those angles as 0, 90, 180, 270, and we could just count by 90s. But in calc, we use radians. We're going to see why we use radians when we get there, but we always use radians. So as a reminder, the measurements on the unit circle are theta equals 0, theta equals pi over 2, theta equals 3 pi over 2, and theta equals, I'm sorry, I just made that mistake. Theta equals pi here. Theta equals 3 pi over 2. And you can keep going. You could also redefine the angle 0 as 2 pi. And basically what we're doing is we're counting by halves, right? If you take out the pi's, we have 0, 1 half, 2 halves, 3 halves, 4 halves, which simplifies to 2. I can keep going and make that 5 halves. We're just counting by halves, but there's a multiple of pi in the whole thing. Hopefully that's a review. No matter which teacher you had for honors calc, that part of the unit circle you have definitely seen. So here's what we have to do here. We're putting two things together. The unit circle is for plane sine and plane cosine. But we have sine of 3x and we have cosine of 3x. So we're going to merge the 3x in orange with the theta values that I have shown on the graph. Our goal here is when does cosine of 3x, or when does cosine of 3x equal 0? Well, that happens when that argument, 3x, is equal to any of those theta values where the first number you see is 0. So that's going to be, the first one we see is pi over 2. The next one we see is 3 pi over 2. And this ends up being pretty easy to kind of continue because you're really just getting odd multiples of pi here. If I had decided to go with one more value here, a full revolution, and then one little bit more, that would be 5 pi over 2. And this list can keep going, and sometimes you do need to make this list a little bit longer. But think about what I'm saying here. If I plug any of these values in, not for x, but for 3x, so if I replace 3x with pi over 2, I have cosine of pi over 2, which is 0. Each one of those numbers coupled with 3x is an equation. So we're going to solve each one of them like an equation. We need to solve 3x equals pi over 2. Then we need to solve 3x equals 3 pi over 2. And then we need to solve 3x equals 5 pi over 2. But we do all of that by dividing by 3. So I'm going to divide each one of those by 3. X equals, well, pi, when you divide something by a whole number, that number just gets pushed into the fraction. 3 pi over 2, or sorry, pi over 2 divided by 3 is just pi over 6. Three pi over 2 becomes 3 pi over 6. I did want to write these in orange, so I'm going to erase those. This separates what an x value is and what a theta value is, a value from the unit circle. So pi over 6, 3 pi over 6, and 5 pi over 6. So now we've taken things that we know from the unit circle, those green values, and translated them into the x values that we really need. Think about it. Take this whole step backwards. If I plug pi over 6 in for x here, I would then multiply it by 3. That would give me 3 pi over 6, but that would simplify to pi over 2. And then when I take the cosine of that pi over 2, that answer is 0, and I have a 0 in my denominator. The way sine and cosine are always going to work is if you have that 0 in your denominator, the thing on top is sine, it's always going to be non-zero. If you're getting 0 for one, you can't get 0 for the other. So with tangent and cotangent and things like that, you're always going to end up with a non-zero over 0. So we know that these are going to give us vertical asymptotes. Vertical asymptotes happen whenever you're in a non-zero over 0. So we have a vertical asymptote at x equals, not 3x equals, so the orange values, pi over 6. I'm going to, as I write this out, simplify 3 pi over 6 to 1/2, or 1 pi over 2. Pi over 2. I simplified the 3/6 to 1/2, which gives me pi over 2, and 5 pi over 6. And that's because 3 limit statements, but we're going to find out they're all the same. Limit as x goes to pi over 6, limit as x goes to pi over 2, and limit as, I don't know why I did that. I'm just going to give myself more room. I'll start up here. Limit as x goes to pi over 6, limit as x goes to pi over 2, and limit as x goes to 5 pi over 6 of my function, which happened to be called h of x, equals. And now here's the last tricky part of these problems. We got to decide whether we're writing positive or negative infinity. We've got to choose a side and decide whether we're going to write positive or negative infinity. I'm going to make this choice all the time. I always choose coming in from the left because it's a little bit tricky with the unit circle. We work counterclockwise around the unit circle, so our values are coming in counterclockwise. Okay. So pi over 6 coming in from the left on the unit circle is, we're thinking about the pi over 2 value on the unit circle. So I'm doing the limit for x equals pi over 6. So I'm thinking about theta equals pi over 2. Sorry, I was underlining that, but you probably couldn't see it. And it really comes to this. I've got to do sine over cosine. I'm taking my x coordinate over my y coordinate. If I am on the unit circle here, both of those things are positive. I'm coming in this way. I'm dividing a positive by a positive. That gives me infinity. Next limit. I'm doing pi over 2, but that's an x. So I'm thinking about 3 pi over 2 on my unit circle, and that's down here. Again, I'm somewhere here on the unit circle. X is my cosine, y is my sine. If I'm in the third quadrant, both of those things are negative. So I'm dividing a negative by a negative. That's going to give me, again, positive infinity. And here's what I think is really nice part. 5 pi over 6, the x value, translates to 5 pi over 2, the unit circle value. But we've already done that one. It's the same question we answered for pi over 2. So that one, because it's the exact same limit as our first one, or the same spot, is also infinity. Like I said, we're going to do this technique, or the thing we're doing here, where we have not just sine of a number or sine of an x or cosine of an x or tangent of an x or any of our functions with an x. We'll do this. We will do this. This won't be the only time we do it. This is our first introduction to it. There are really 2 parts. You have to read the values off the unit circle, and then you have to solve those equations to get your x values. Once you have those x values, you have your answer. If you can get yourself to that point and feel confident with it, I think you're in good shape. Getting these infinities, especially with me not in front of you to pause and say, hey, do you have a question? Do you want me to go over something there? I think that is tricky. But that is how you do it. There is one problem in the assignment that it's similar. There are going to be a couple changes to it. It's going to be secant. Secant is 1 over cosine. So when you go and do your infinities over here, your numerator is always going to be positive, but cosine is positive here, but negative here. So you won't get 3 matching infinities. That being said, we can go over that in class on either Friday or Monday. We'll revisit that. We'll revisit this math a couple of times, and you'll just have to practice your way to it to feel like you're being good, to feel like you're good at it. With that being said, there's only one problem on that one. The rest of it is for the most part making sign charts, identifying x values where your asymptotes are. So take the rest of the time, the remaining half hour, and get as much of this done as you can. And I will look to take questions on it tomorrow and then collect it. Oh, you can also, I'm glad I saw this, I'm glad I scrolled, cross out number 11. I don't need you to do a factoring where it's not x squared at the front. I used to try to practice that more, but I realized they very seldom have you do that on the AP test. So don't stress yourself out on a difficult factoring problem. Okay, we will see you tomorrow. That's about it.